Okay, welcome. This is my talk called Malloc Alone. You all know this movie, right? Yes, How to Resist It. Okay, the talk is going to be divided more or less in four pieces. The first one is not critically, but it's not critical by itself, but it's very important to understand the next three, and the next three are going to be really important. My goal in the talk is to get you curious, or at least at the very minimum aware that these things exist. Like very often we use the garbage collector or Malloc and stuff, and it's all magic, like yeah, Malloc free, who knows what's going on. And I don't want it to be magic. So it would be awesome if at the end of the talk you come back to your desk and you Google this stuff and you try to find documentation, find some experts. I'm not an expert myself, but if you ask me, that's the best way of me becoming an expert, me trying to help you, so please ask. Let's start. So we have a little Malloc Kevin, and he's in the world with other programs like Vim and Emacs, choose yours. Windows, don't choose that one. Anybody knows this one old messenger? I know that you used to have Gadu Gadu, the Polish people, but like we, like from the West, we had messenger when it was like this size.
ICQ or something?
Sorry?
ICQ?
No, it belonged to Hotmail. It was like, you know, Facebook Messenger today died many years ago. And then we have here little Malloc, and he's living in the world with computers, and he wants some RAM. And he said, let's take a bit of it. Okay, now I'm going to put my data here. Fantastic. Malloc gets his memory. And then the evil cousin comes and says, hey, I want pointer 0005 address complicated. And Malloc is like, hey, no, I'm using that. Why do you want that? And evil cousin says, I don't care, what do you say? It's mine now. This is a problem. Poor Kevin, somebody stole data from him. Like his password, something sensitive. We have third programs that have access to the private data of an initial program. This could be, you know, Firefox suffering and a virus stealing the data when you enter your bank account. And this is not nice. So how does it come that programs are protected? So Kevin, Malloc is really Firefox, call it what you want, he's really mad, he doesn't want to see them ever again. It's a pain in the ass. So here comes the kernel to help. I'm gonna put examples from Linux because mostly it's open source, so I can see what's going on. You know, you just read the code. Windows, God knows, but should be fairly similar with different names for the function, but should be a very similar spirit. Kernel comes to help with virtual memory. How does this work? The kernel has to lie to our programs. Every time a program asks for a piece of memory, the kernel is going to say, yeah, okay, but I'll give you something else. The strategies can be very complicated, and the kernel has to bookkeep. It has to keep tables of data and data structures of what address belongs to whom, with what permissions, and so on. Kernel has a really complicated job, and the idea is going to work a bit like this. So, give me address, whatever, 45DXE0. And kernel says, sure, 1 second, this all comes with help of the processor, by the way. 1 second. Kernel goes to his memory tables. He says that Firefox is the program number 1, random number. And he goes to a process table in which he has each program, and he sees the address of the memory tables of that program. And from there, has like all the programs over there, and then he moves, and this is the data structure where he has all the data for this process. And then the kernel says, okay, address 45 lines on page 45. This is a simplification, but just to get the idea. He goes to the table, page 45, means offset 19. So the kernel says, oh, so Firefox wants address 19, BAXE0. It's more complicated. This is a simplification. It's not really like offsets and so on. It was like that at the beginning, but technology evolved and optimizations are extremely complicated. So the kernel says, hey there, take here the contrast of address. I will tell you in it was 45, blah, blah, blah. But you will never know, and you are not supposed to know, not you or anyone else. If anybody in the entire computer knows, the kernel is broken. You can steal data from each other. This has something uncomfortable. What is the pain here?
The performance cost of bookkeeping?
Yes, yes. It's a kernel. I mean, imagine the operating system is slow. That's the most horrible thing. You would hate it. Like anything can be slow, but not a kernel. So, what data structures to use for optimal page tables of the processor, of the process? Imagine that, for example, a process is not going to need the entire memory, the 64 gigas of RAM, some people have 32, whatever. If you have to keep a table for the entire memory address for every process, you would just spend thousands of gigas only on the memory tables and not in the processes themselves. So the memory tables are going to be lazy, they are going to initialize only as needed. Then every reference in memory, you have an address that has a pointer that goes to the other, that goes to the other, that goes to the other. Imagine that the process just said, hey, give me address 45, blah, blah, blah. And in reality, you are going to memory 7 times. And that's going to be painful. This has to be massively optimized. That's why I'm not going into details, because it will take me a week, a year to read it myself, and then a week to tell you. So just so you know. There are many strategies. Some of the most popular I have written here are inverted page tables and multi-level, which is just lazy initialization and then optimization of how to find the data. As I say, I cannot double the indirections. So there is in the processors this special chip, the MMU, Memory Management Unit, that became very popular in Intel for having problems with Spectre and these vulnerabilities that came out a year ago. When the processor sees that an instruction says, give me address, blah, the processor has in a small chip inside of the processor, this memory management unit, a few of those tables. And the processor will try to optimize everything. This would be virtually okay, just to go to this table safe inside of the processor and dereference and check the real address and then load the real address. But those tables have finite size. And the kernel, with the help of the processor, they have to take more strategies to optimize the best addresses, what are you going to need later. If the address is not in this memory table, the kernel raises an exception, the processor raises an exception, kernel checks, is this a valid address? Okay, load this new memory table in the memory management unit. Takes an eternity. I mean, I find amazing that computers are fast with all the stuff that they have to do. So, this is a super complicated disaster. It's like a spider in your face, this movie. Okay, so time to wake up. Everything is solved. Okay, everybody will have just whatever he says, address 5 would be a different thing. And so, Malloc goes out, and sounds, voila, he's alone. He can take all the memory he wants. Nobody will steal it from him, as long as the kernel is not broken, of course. What about your responsibilities? Okay, now you have 16, 32, 128 gigas of RAM. Here comes the action. What are you going to do with all of that? How do you organize this problem? Responsibilities, little Kevin has to go and do the shopping, and shit can happen. And so, this is where allocators come. Here is where we are going to get into relevant and useful things. The kernel says, if you go nonsensical, I think I should better kill you and you save time and resources. The kernel is going to try to protect that precisely processes don't steal data from others and so on, and the kernel is always going to play safe. And so, but what does nonsensical means for the kernel? Question for you. What can go wrong with a pointer? You have a pointer and you want to see the address. What can go wrong? C++ programmers, come on. What can happen? Yeah?
You can go a wrong place, but not in this case.
Yeah, well, what is your classic program? You have a pointer. The first thing you learn in the second day of class
You forgot to unallocate.
Yeah, for example, you
Or you can try to access something which is not yours. For example, incrementing it too much.
yes, you can go a buffer overflow. You can have a what is the error you usually get?
Null pointer exception.
Null pointer exception, that segmentation fault. Okay, three things that can go wrong with a pointer. Use after free, free after free, and forget to free. Or use without ever allocating, which that's like really bad. How does the kernel know that you did one of these three? The point is the kernel doesn't know you did this one. Like if you forgot to free, it's a memory leak. The kernel, it's not a genius that can predict the future. And actually, guessing this is equivalent to the halting problem. And you know the halting problem doesn't have a solution, so there is no way the kernel can guess if you will ever need a memory. That's your mistake. But the kernel can protect you for these two, more or less. Use after free and free after free. How? Precisely through virtual memory and the memory tables. The kernel is going to load the pages lazily. And if you ask for an address of which there is no page, the kernel will say, yeah, no, that you shouldn't ask for this. You're making a mistake. So, your allocator Malloc knows he's being observed. And he also has to play with this idea. How this would work? You remember this diagram? This is your memory space of your program. You make a program, execute, and the operating system kernel will load in the entire memory space. At the bottom, these processor commands, initialize data. This is usually the actual binary, the instructions. And there at the top, you have the command line argument, environment variables that the kernel is passing, and then you have the stack that starts growing down, and the heap that grows up, and you remember this like from school or something. This space is unprepared. It's unaware of the outside world. It's vacuum, empty. It's a disaster. It's this dark place that we have to prepare and take care of. How do we do this? We just start growing continuously from the bottom. Okay, in the presentation this is cut, but this was just text, data, terra incognita, because nobody knows where is it, and the environment, and the stack. Usually processes have stack size, depends on the implementation, could be a mega or 8 megas, depends on how modern and powerful your computer is. You can send a flag to the process, to the operating system before loading the processor, hey, give me a bigger stack, but it's usually a default. The operating system has a memory table prepared for the stack, for all of it, the 8 megas or whatever the operating system initializes. But all of this doesn't have a table. And it works something like this. Malloc of size, 1024, you say, okay, 1 second. Kernel, give me, and this is a POSIX function, that I think in Windows was like virtual alloc something, but the idea is the same. It will just have different names. RBK. What does that mean? This is the program counter. Like this is data that you have, instructions, constants, global, static, and everything. And your program will start allocating memory from here, from this point. And this has an address of the end of your program. RBK means just move this top counter a bit higher and prepare tables for me here. So the table says, yeah, sure, here you have. Here you have a few, and then let me bookkeep this for you. The allocator, not the kernel, but the allocator inside of your program does some bookkeeping and maybe an adding list. The user piece is ready, and then he gives a piece. The operating system has no idea if you're using this one or that one or whatever. You just loaded all 4. Next one. Malloc of a much bigger number. So this doesn't fit in these remaining 3 spaces. I need more. So kernel, give me a map. Again, in Windows, different name. This is a memory mapping of a much bigger memory space. The kernel says, yeah, sure, here you have, somewhere, random. And let me go keep this for you, linked list as before, and my user space is getting ready. Here you have, ready at address, blah, blah, blah. Make program continuous. And in your program, you say, read the reference pointer, name of the pointer you have, plus, and you know the buffer overflow. You go farther away from what you allocated. And says, yeah, your requests are orders. And he reads this memory. But you never allocated this, you never use it. And there is no way the kernel knows if you're using this one or that one, so there is no segmentation fault here. You just hope that there will be a segmentation fault, but there won't. Maybe this was allocated by a different program, maybe you will allocate it later and now you have an alias. This is undefined behavior. This is the kind of things that the C manual says, if you do this, it's your problem. It cannot help you here. Okay. Free that address. Okay. Now the allocator has to remember how big was that address that he allocated for him. The size was 1,000, the number from before. Okay, yeah, this pointer was of size that one. The allocator has to keep track of the sizes. Cool, so I know how to do that, free. And then the allocator says, hey, I actually don't need the entire chunk anymore. Kernel, memory on map this, please. And the kernel says, yeah, sure, thank you for being a good citizen. And this is how you give memory back to the operating system. Like, if you have the entire segment but you're using only 1 byte, you will not give back the entire segment. That memory is used. And so now, you happen to, use after free. And read address, I hope you know what you're doing. Okay, kernel, no. No, I don't have memory tables for this. You freed, you return it from me. Now you made a mistake. I'm sorry, no, die. And this is the end of your program. This is how the operating system would realize that you make a mistake. It's undefined behavior. You're not sure if you're going to have a segmentation fault at the moment, which would be fantastic because you know where the problem happened, or the seg fault will come much later. And then you will have a lot of corrupted data program. You just wish for the best. But it's undefined behavior. Now, what's uncomfortable here? And there are 2 things actually that are uncomfortable.
First of all, the process dies without the possibility to save changes, for example. It's very bad.
Yeah, for example. Yeah, something else? One first question is a bit more simple. How does the bookkeeping works? When the piece that you have allocated from the operating system, the kernel gives you these 4 megas, and how does your allocator, your Malloc, knows? There are many implementations, but the most popular one, the one that really won, it's the linked list idea. So basically every chunk will be divided in the memory that you're actually using, and before there will be a word size of the size of the allocated memory. This is how free knows how much to deallocate, because he just dereferenced the previous address, and then he sees the size and he knows that all of these should be returned. And this is how free works. When this is not used, the kernel keeps this with pointers to the next blocks and the size of the next blocks inside of all this chunk. If the chunk is very small, these 2 can be not used, but you always need size and 2 pointers. This is always needed. But then the strategies can get incredibly complicated. I mean, these chunks can be of, 8 bytes or 20 something or 64 bytes, whatever. Or more, what if you make a request that is very big and then you have to glue many of these chunks. You just allocate all of them and put here the size, the final size. If you free a really big one, should you divide it in smaller chunks again or not? What is the best strategy? gonna get really complicated. And precisely, what is the problem again? Gregor? Bookkeeping, yeah, and the keyword starts with P. Performance. How big to pre-allocate? You know, when you do SRBK, the kernel, I mean, you requested 1 kilobyte, but should I ask the kernel for 2, 3, 4, 1? Those system calls, every time you go to the kernel, that's also very slow. So you don't want to make system calls all the time. You don't want to do SRBK or mmap all the time, because those are very expensive. That basically means saving the entire stack, give power to the kernel, change a lot of memory tables, takes a lot of time. So you don't want to do them all the time. So how big to pre-allocate? When to give back to the kernel? What about fragmentation? You know, allocate, free this one. Now you have these two, this one is free, and you request something bigger. So this space you cannot use it, because you need something bigger than that one. So how to solve the problem of fragmentation, or serving different request sizes? Cache locality. You have heard of this. When everything is contiguous, the processor is faster. So how to promote that the cache is going to be contiguous? And this can be interesting when you have very specific cases. If you have a memory-hungry application for structures of constant size, imagine that you have, for example, I have some programs cut with some audio, and I'm allocating a structure that has all the data for the call. And I'm just doing new and free of the same thing all the time, millions of times. It's not sometimes bigger or smaller. I'm always allocating the same size. So one of the most popular strategies for a standard generic malloc is to have a few linked lists of different size. A linked list for things of 1 kilobyte, another one for things of 2 kilobytes, another one for things of 4 kilobytes. If I'm always going to allocate 2, I don't need all the other linked lists. So I can customize and improve performance a lot. This is very complicated, dangerous. Do it only if you really, really, really need it. Otherwise, the chances for a mistake are really big. But you can get so much performance. If you know in advance the patterns of allocation, if you know that you are going to need exactly 2 megas, you can map from the kernel 2 megas from the beginning of the program, and then you can save all the memory call, the system calls for later. This is a chance for a lot of optimizations, but also can get really complicated. Here you have some links. And of course, what about multi-threading? You know, if you allocate something in your linked list, 2 threads, say malloc, you have to put a lock and so they don't collide, the allocations. But then locks are also, they hamper performance. So should you have 2 different heaps for the 2 different threads? But what if one thread is allocating things all the time and the other one doesn't? Then you have a heap that is wasted. How to improve all those many details. I have seen programs where I have like 20 threads, but there is only one allocating things. Doing a lot of crazy malloc free all the time, and all the other threads are just having static memory. But the standard generic malloc prepare heaps for all of them, so that's a lot of wasted memory. For example, so again, this is like a spider in your face. It gets complicated. So, let's come back to the root of the problem. We have these 3 cases. And the question is how to avoid them, and how to not to have these problems. What solutions do we have?
Smart pointers.
Yeah, that's an option. But before smart pointers, what is what basically everybody does except C and C++?
Garbage collection.
Yes. We're gonna go there in a second.
The question, what's wrong with free after free?
Free after free, yeah, that's a good question. I actually didn't... let me come back to one of these. For example, here. We have this memory, and imagine you free that one, okay? So, and then you give it back to the operating system, because you don't need the entire map anymore, and you give it back to the operating system. When you free, the implementation of free tries to do this. read the previous size to know how much to free, but this doesn't belong to you anymore. So exact fault. And the second option, the second thing that can happen, is that you free it, but someone else malloc again. And then because this is free, he can give this address to a different process, a different object. So when you free it again, you're freeing someone else's object, and then you corrupted someone else's data. Which is even worse because the problem will come much later, and then this is very hard to find problems. When there is a problem, you want it to detect instantly. Then it's a lot easier. I mean, it's painful, but much less. So, we have... what are we trying to find? Like, we're going to go into garbage collectors, but what is it what we're really trying to find? Pointers that we don't need anymore, exactly when we don't need them anymore, and without confusing later that, oh no, I needed it in the end, I'm sorry, give it back, that cannot happen. So this is zombies. You can call it living pieces of memory and dead pieces of memory that haven't finished dying yet. Like, what is dead? A piece of memory. Dead means that you will not need it again. But from the moment you don't need it anymore, it becomes a zombie until you finally free it and give it back. Then it's finally dead. So you're trying to find zombies. That one that you don't need anymore and you can get rid of it. But there is a problem. Again, as I said before with the kernel, this is a funny quote from this book. I find it mind-blowing. The undecidability of liveness is a corollary of the halting problem. That means the halting problem doesn't have a solution, and as a corollary, this also doesn't have a solution. There is no way to always know if a piece of memory is dead. It's unsolvable. You can do manually some cases, but there is no algorithm that will always solve it, and there cannot be. That's the point of the halting problem. That in a million years with quantum computers and so much better mathematics, we will still not have it. It's a theorem. It's impossible. But it can be very well approximated by a decidable property. Reachability. Reachability. This is awesome. What is this? Like, what do you get from the world? That you can reach it. Right? That you have a pointer that can arrive to this piece of memory. If you cannot reach it, probably you don't need it anymore. So reachability, just mathematical definition, is a preorder. It's reachable from another object if it can be reached by following a chain of pointers. So with this idea of the chain of pointers, we can form a directed graph. Objects are nodes, pointers are the arrows, and reachability induces a preorder in this directed graph of memory. And what is a preorder? A binary relation that is reflexive and transitive. Reflexive is I can reach myself, and transitive is if n reach n and n reach O, n can reach O. It's very intuitive. With only these two properties, there are entire books. I had an entire semester in university studying this. There is theories about category theory and homotopy type theory. It can get massively complicated with such a simple definition, but there is a lot of things we can do from this. A preorder is a very, very weak graph. If we put more conditions, you can have stuff like trees or a cyclic graph and so on, but you have to put a lot more restriction. This is like almost the minimum that makes some sense. What is this good for? So you have your memory graph here with A that has a pointer to D, it has to C, B to A, A to B. Here you have a different component. If we have the entire memory, everything that you have ever allocated and deallocated, you can explore these kind of graphs and divide your components. And there are special nodes. There are two exactly that are really, really special in this map of many nodes and arrows. So, any idea? When I was explaining the program before, there are things that the kernel allocates before the program starts execution. The heap will just be prepared on the runtime, but there are two things, one on top and one on the bottom, that are allocated from the beginning. One of them is almighty and super awesome. It's the stack. And the other one is data. So globals and constants and so on. Those two are the ones that are gonna dictate the execution of the program, and they are the ones that are going to create new nodes or get rid of them. Receiving data, those are constant, they are globals, and they are not always globals, but they are static data from the beginning of the program. So that one will probably never die, but they can have pointers to other stuff that can change. And then the stack, execution. Garbage collectors. So this is our wall. We have memory with maps, with arrows and graphs, and we are going to find a tool. The garbage collectors start here. These are two papers, both from the same year, from 1960, a very productive year, by John McCarthy and George Collins. John McCarthy is this guy. He's a very cool guy. He's in the previous paper, it's one of the most important papers in the history of computing. In like 10 pages, he created leaves and garbage collectors in prehistorical time. This is like archaeology. If you read the paper, you wouldn't imagine that that is a garbage collector, but that's where it all started. And this is a cool guy. He was working in artificial intelligence. He's teaching his computer to beat him in chess. Isn't that cool? If you are not excited about this guy, he's awesome. You see, the idea works something like this. Unfortunately, the projector is a bit yellow, so you don't really. I hope you can read. I don't know if you know Lisp. Lisp means list processing, and in Lisp, basically everything is a linked list, single linked list. Absolutely everything is a list with the next allocation and the next allocation, and you can have very long lists and so on. And there is one thing in Lisp. When the program runs out of memory, the garbage collector, he didn't call it garbage collector, but the garbage collector will stop the program and check what's going on. The idea is something like that. We just do new cell all the time. A new one, and a new one, and a new one, and a new one. And you can see cell, allocate. If I allocate a null pointer, that means the allocator didn't return anything. That means now we run out of memory. Otherwise, we just return it. Here you have a pointer to a new cell. If we run out of memory, then we have to clean. And how do we clean? We prepare a word list. We go through this graph, starting at stack and data, the roots, they are called roots. Starting from there, and we mark everything that we can actually reach. And this is the step mark. And the second step is sweep. Once we mark everything, we just put a reachable, a 1. Once we mark everything, we go through the entire heap a second time. And then we just see, okay, this has a 0, that means we never reach it from the stack and data. Free. This has a 1, keep it. 0, free. 1, keep it. The idea is something like this. I made a very simple implementation of mark that is recursive. That's why worklist is made before. This is ugly C++, sorry. We have the roots, and for each one of them we get his address, and we see if this address is marked. If it is not, we mark it, and then we add to the worklist all his children's, and then we recurse. And that way we just go through the graph and mark all the kids. Like reachable, 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 reachable. At the end, okay, let's kill everything that is not reachable. If in the end we just allocate again, if it doesn't work, that means that we really run out of memory, so through an exception, but we run out of memory. And the sweep is this idea. We go through the entire heap from the beginning, and until the end, if it's marked, just remove the mark for the next time. If it's not marked, free it. The next piece of the heap. The other idea from George Collins, also coming in the same year, is reference counting. In the tracing garbage collector, in the mark and sweep, we will arrive to a node as many times as that node has pointers arriving to that one, so other people know that this pointer exists. So the second idea is to be more incremental. You go step by step, and basically every time somebody has an arrow to the node, we just put a +1. because that means there is one person who needs it, and then you copy it, okay, there is two persons who needs it. And then when somebody says free, we just say -1, and if it's still not 0, we keep it. Once we say it's 1, and we say -1, it's 0, we can free it. So as we can free it, that you have memory that goes out. So the idea is a cell, you allocate it. If the allocate doesn't return, you can just throw an exception that will die. And you set the ref count to 1 and return that cell. This is a cell that has an extra field, the ref count. Then when you free it, what you do is to remove 1, and if it's equal to 0, free it. And once you free it, go to all of the childs and set them -1. You understand why? If this one is free, this one that has an arrow, now he has one owner less. So you can count one less. And this one, if this one has a 0, you should also free it. And then that way you can free the entire chain. And when you copy the cell, you just make a new cell, copy the data, copy the ref count, and increment the ref count. And return this new cell. This was done in the 60s. I mean, I don't know if C existed this year. Maybe in a very... which year is C? I forgot. I think it's from the 60s. Unix for sure didn't. Actually, yeah, Unix was before C. So for sure C didn't, and Unix maybe. So, a problem, a super important problem of reference counting is that these kind of problems can happen. This C has a ref count equal to 2. There are 2 arrows going to him. Once you do in your program this bit that is in your stack and you say destroy the children's, you just remove the pointer, now instead of 2 is 1. It's not 0, you don't get rid of it, you don't deallocate them, you have a cycle. They are all keeping each other alive. So you will never deallocate them, but this is virtually lost. I mean, you will never access it again. If your stack doesn't know, it's lost. So this is a disadvantage of the reference counting. It doesn't catch cycles. But on the other hand, it's incremental. It's not, at the end of the day, let's stop the program and spend half an hour cleaning. This is a comparison, their properties. Reference counting is incremental, tracing is a batch style. At the end of the day, clean everything. Reference counting is clean as soon as, one by one. Cost permutation tracing, it's none, but reference counting is high. What does this mean? When you do +1 in the ref count. Like you're only accessing or making a copy, but you have to do +1 in this ref count. And multi-threading. So when you do +1 in the ref count, you have to synchronize all the threads. So that's expensive. Post times, this is a classic critique. Everybody who has done Java or C# or whatever, you know that sometimes like out of the blue, your program can stop because garbage collector is running. It's real time. The reference counting, yes. As soon as something goes out, it cleans it. But the ref count doesn't collect cycles. The idea of ref count to solve the cycles, okay, you don't catch it, so you have to do a second round through the heap. And that's like making the reference count a bit poorer. But tracing is actually doing 2 rounds on the heap anyway. So it's not that it's worse or not, it's getting closer to that one. And the idea, the catch, of course we have to optimize these algorithms. These 2, tracing and ref counting, these are really archaeological, you know, 70 years ago, I don't know how to count. 69 years ago, something like that, I hope I'm saying it right. That's a long time ago, this is very archaeological, but you get massive optimizations and mixes, and get very complicated. But the idea is that they are very similar. That there is like once optimizing one means getting it closer to the other. Optimizing this one means taking ideas from this one. Like solving the idea of the ref count that doesn't catch cycles is doing a little bit like tracing. This is what Python does. Python is a ref count program. Everything, absolutely every allocation is ref counted. And every once in a while there is a garbage collector that runs and does the tracing just to catch cycles. A super, super simple implementation is the worst performance. That's why Python is so slow, but it's super simple to implement as an implementer of the language. It's the easiest one. Ref counting, the problem of mutation has one important problem, that the stack, you enter a function and you leave it super, super quick. The stack is mutating very, very quick. So you will do +1, -1, +1, +1, +1, -1, and every mutation is expensive. So why doing all those mutations? If you can defer them, if you can do them later, but then do them later means you are not incremental anymore, you have to trace them. At the end of the day, you have to check all of them. Ref counting is traversing the dead objects. Once you have a 0, you go and kill all the children. And tracing is looking for the alive objects. They are a bit like dual. What else? The extra interaction is the sweep. Here the trial to catch the cycles. This graph, this table, I'm actually taking it from this paper. This paper, a unified theory of garbage collector. This is a paper from IBM Research in 2004. It's beautiful. Everything you will ever need to know about garbage collector is in 20 pages. It's really dense. It's not easy to read, but it has almost everything. It has really detailed descriptions of really optimized modern garbage collectors. See? And the idea is optimize and optimize. Of course, trace segments of memory incrementally. That's a thing that tracing can do. Instead of tracing the entire heap, you can trace only a segment and later the other segment. So there's less stuff to do. But if there are cross-references between segments, you have to ref count them. For example, this is an amazing optimization from tracing. Objects often die young. You allocate it and very soon you kill it. If you haven't killed it in a few milliseconds, it will probably live for a long time. For example, the .NET garbage collector is a 3-generational garbage collector. So you create everything and put it on the first generation. You run the garbage collector only on the first generation. If it survives, you move it to the second. Later, you run the first. The second generation, you don't run it as often. And if it survives the second generation, you put it on the third. And the third generation garbage collector, you run it very rarely because statistically, empirically speaking, doing tests all over the world, if it lives for a long time, it will probably live for a really, 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 really long time. So you don't need to kill it until much later. But then, cross-references between segments, you have to optimize those problems. And an optimization for ref counting is defer the mutation for later, but then you're doing a bit like tracing. So here's where this paper comes. Okay, not a spider in your face. Really complicated. Small parenthesis. This is a piece of code that I actually had to solve last week. It's a bit edited, so it's easier to present. The idea is like that. We have this Windows thing, result. We allocate a filter, taking the address of that thing because we're going to mutate it, and then we check that the allocation works, that it didn't return null pointer. This is already problematic because malloc returns 0 if it fails, but new returns an exception if it fails. This code used to be C, but somebody just changed it to C++ and it didn't really...
You can modify the code in you.
Sorry?
There is a keyword like not raw and then you want raw.
Might be. But I didn't see it anywhere in the compiler. I think this would throw an exception, but the problem is worse than that. This macro. This is a Windows macro from the Windows API, also very old, and it's a macro. Say succeeded. What is this macro? Definition is like this. Take a macro, we cast it to a result, and then we see if it's bigger than 0. The idea, if it's in the Windows API, a negative result would mean that there is some error. What is result exactly? It's a type def. It's a result is all of this as long. And this is more macros, and then you can go to an infinite chains of macro. What is this? What is this? What is this? What is this? It never ends really. Windows is weird. What is the problem here? The problem is that in Windows, long is 32 bits, but I'm compiling to 64. So I'm taking this pointer and casting to long. Also, pointer is unsigned, but long is just long, it's not unsigned long. And my question was, when I discovered this problem, is why was it not failing before? This is a code that I had to change. I changed some things in the compiler for a new version. It was using a very old .NET with a compiler from the archaeological compiler. And I was just making it compile with a new compiler, and I just wondered, why was it not failing before? I mean, it was already 64 bits before. It never failed. This was in production for years, and it never failed. But it's obviously wrong today and yesterday and 20 years ago. Memory ranges of the allocator and the garbage collector. You remember the map of memory? In the implementation of this Malloc and the garbage collector, somebody decided to give Malloc low addresses and the garbage collector high addresses. So if it's 64 but it's a low address, when you cast it to long, it's still okay. And that's why it never failed. This is Windows, so there is no way to know. I cannot see the code, but I tried to make some testing implementations and just to see the memory mapping. There are debugging applications in Windows that can tell you where the heap is allocating and where are you calling the equivalent of mmap in Windows, virtual allo with parameters. And I discovered that in the previous .NET, Malloc was always getting low addresses and garbage collector was always getting high addresses. Not only that, this, of course, I haven't seen the code, so I might be wrong in a super edge case, but with all tests that I did, not only that, Malloc was only doing SRDK, was only growing here. And the problem of doing SRDK, you remember in the previous slide, when you grow from the bottom, you do SRDK, 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 SRDK. If at some point you free everything below, but you're still using the last one, you cannot return the entire segment to the operating system. And this is one of the main disadvantages of a very simple SRDK, just growing the program counter. If you're using this one, all of this is free, but you cannot give it back. So it's sort of lost memory. So this, like, the guy from Microsoft who decided to put Malloc in low addresses only by SRDK, like, why? But, well, garbage collector was taking high addresses. In the new implementation, it's all mixed and really well optimized, so sometimes was failing, sometimes was not. And this wasn't driving me crazy. Why so random? I don't get it. A pointer. Okay, you know, pointer sometimes has different addresses. Cast it to long. Yeah, okay, I see. And then I run my test and okay. And the last question, with time? 5 minutes. The last question is, can we achieve deterministic, safe, penalty-free memory management? You know, the garbage collector, you don't need something anymore, it's a zombie, but it can take hours until you finally kill it. And then through all this long time, it's not deterministic, you don't know when, and it will probably be much later. And it also steals a lot of performance. So the question is, can we do a bit better? Can we make sure that it's safe, but without all the disadvantages of the garbage collector? This is a really old quote. C programmers think that memory management is too important to be left to the computer. Lisp programmers think that memory management is too important to be left to the user. This is a quote from Sustrap when he made the first manual of C++. It's a very old one, but still so valid today. Sustrap is still criticizing garbage collectors. How to do this? This is the first idea of C++, and for me, this is the idea of C++ against C. It's not object-oriented, that's really poor and boring. That's a small, it helps, it has some utilities. But this is the massive evolution when C++ improves so much. The first thing that C was doing actually was the stack, but then C++ added the value semantics, and much later the ownership. The life of a resource is very, very often determined by the life of a stack frame. You know stack frames? You call a function and there is a new stack frame for this function. And when you finish this function, the stack frame just gets forgotten. It's removed from memory. You just put the top of the stack here. And this memory is automatically free. The problem is that C would consider all of this stack frame as all values. Like you're getting rid of an integer, that's fine. You're getting rid of a pointer, it's fine, but it's not really. The pointer has an address to something else. So the idea, a stack frame deallocates everything as values, whether they are values or not. So the idea goes something like this. This is an example. You have a struct with a pointer. You make this struct with, you initialize some values. The pointer you malloc something, and then you return this one. There can be more steps here in the middle. This is just an example. And then you finish the function. When you arrive here, the runtime will just forget about all of this. And this pointer is lost. Like you clean the integers, and you clean this struct, but you didn't clean what was outside. Because you are treating it as a value, but it's not. You are not treating it as a value when you should. So the idea of C++ is you have this struct. Instead of writing that, write it like this. You have a constructor that will allocate the memory, and you have a destructor that will free it. And the C++ compiler will do something like this. Actually, the first C++ compiler was a translator to C, and it was literally doing this, really. Today, not anymore. There's massive optimizations, amazing, complicated stuff, but the idea is the same. The original C++ was just translating, syntactically, just changing keywords. And it was something like that. You have the same struct that you have before in C, and these two new functions that take the pointer. The famous this is just an extra parameter to the function. And the compiler will also do this. You have this old function. You should do free before exiting. You should, but you can forget. Or even worse, there can be an exception in the middle, and then free will never be executed. So instead of writing that, you write it like this. In C++, you say you allocate it here in the stack, and you change the values, whatever, and then you return what you wanted. And the compiler will do something like this. When you create the function, the compiler injects the constructor. Then your instructions return, and before exiting, injects the destructor. This is not valid code because whatever you write after the return will never be executed. But so you get the idea, this is what happens. This is the magic idea of C++, treating as much things as possible as values. We just inject this destructor. And I have a link here for you, just to show you. I have this code here, but this thing is cutting it. This is the code that gets executed, that gets compiled. In main, okay, it's not this. In the function, main just calls this function. And in this function, you have this t and return ta. It's the same code from before. What the compiler does here in f is initialize the stack, allocates the memory for this t variable, and calls the constructor, giving it the address of where this is. Then, once the object is constructed, he moves the value that we're going to return later to a special register. He calls the destructor, he rescues the register that we have to return, and then we exit. This is how code gets compiled. The destructor is injected, always, even if there is an exception. And this is also something beautiful. If there is an exception, when you start unwinding the stack, for sure it's the definition of the language. You will call all destructors.
So does it also mean that the compiler would kind of inject exception handling. Or
Yes.
It's missing.
Yes. That's implementation defined, and in this case I actually know the Windows one better, and yeah, the compiler is just injecting a lot of exception handling, but kernel exception handlings to tell the kernel, wait, don't kill anything, let me clean, and then you continue killing. It's a bit complicated one. So, this is called resource acquisition initialization. In the constructor you create it, and the name is not really clear. In the destructor you clean it. So, but we should better call it resource are bound irreversible to scope, because rabbits are cool. Rabbit. So a resource it depends, it's bound on the scope. Once the stack leaves, you can get rid of the resource. And now, one last thing, we are talking about ownership only halfway. Because we still have a lot of open questions. What happens when you still have a pointer? When you don't put it in a constructor and destructor? What happens with file handlers, for example, that they are not really pointers? Like the whole idea of object-oriented things in C++ is that you can make the constructor and destructor, but there are things that are still not values. At least not imposed by the language. You should. The language is giving you facilities. The idea is, what is natural ownership of an object containing another? Just put it as a variable inside. You don't even have to make a pointer. You can just put it inside. But what is a natural ownership for a decouple or for a return value? When you return a vector by pointer, and then who has to delete this pointer? You put it on a constructor and so on. The idea of putting the pointer inside of an object that will clean it later is precisely the idea of unique pointer. If there is a single clear owner, then as soon as that owner goes out, we know when to clean this memory. If there is one. If there is more than one, we can ref count them, like the reference counting thing. And what about just borrowing? When you just want to use the object but you don't own it, you're not going to destroy it or anything later. So, quick example, because it's time. Once the owner is free, you can clean the resource. And the idea is like this. You make a unique pointer, and if you give it, the compiler will tell you no. You have to move it. That means this morning, the pointer, you will write null pointer, so now he doesn't have it anymore. And in the one that goes inside of the function, you will write the address, so the function will destroy it. You're giving the full ownership. There is only one owner at a time. So you can give it to the other guy. If you do this, it won't work, because you already moved it here. The problem about C++ is that the compiler doesn't complain here. When you do the second move, the compiler doesn't tell you. This is complicated because of retrocompatibility and a whole mess. Rust is a language that would compile here. 1 minute. So you can borrow it. Get means give the real pointer temporarily. But if the function inside deletes, shouldn't, but again the compiler doesn't complain. So this is all convention. This is what you should do. But this is the abstraction. You borrow it, you use it, but then it's still mine and I will destroy it later. There's only one owner. And pretty much, in the end, Malloc grew and turned into a share pointer. When there are many owners, you have to ref count them, but remember ref count, you have to synchronize threads, you have to catch cycles, that's why in C++ you have weak pointers, and the whole ownership idea grows. This is the end. It's a last joke for you. Any questions? Although we run out of time, but you can always ask me in the corridor or in the email. Any questions? Did you like it? Thank you very much.